Good morning students, I am Krina Dayani and I am your chemistry teacher. In our chemistry lectures, we are on the fourth chapter of our chemistry, that is structure of atom, and we have gone through so many topics in this chapter, and we are about on the last topic of this chapter, that are quantum numbers. In the previous class, I have discussed about two sets of quantum number, that is principal quantum number and azimuthal quantum number. Now in today's lecture, we will discuss about the magnetic quantum numbers and spin quantum numbers. So we have our third topic, that is magnetic quantum number. Now, what actually are the magnetic quantum number? We have discussed that the principal quantum number will tell us about the shell of an atom. Azimuthal quantum number will going to tell us about the subshell of an atom. Now, if we want to determine the orbital of an atom, then we will go through the magnetic quantum number. The magnetic quantum number has been proposed by a scientist named Zeeman. So, it is discovered by a scientist named Zeeman. Secondly, magnetic quantum number are represented by small m. Because these are magnetic quantum number, we will represent these by the symbols small m. Now, our third point of consideration is, it is discovered by Zeeman. Its symbolic representation is small m. What does magnetic quantum number tell us about? It will tell us about orbitals in a shell or subshell. So, magnetic quantum number will specify the orbits in a shell or in a subshell. So, we will know about the quantity or the count of the orbital according to the magnetic quantum number. So, what actually the orbitals are? Orbitals is a three-dimensional space in a region where the finding of electron has the maximum capability. So, I am writing here what is orbital. The term orbital we have discussed in our previous lectures. So, what are the orbitals? Orbitals are actually three-dimensional regions. Orbitals are three-dimensional region in which finding the probability of the electron is maximum. Finding electron is maximum. So, it is all about the term what is orbital. Now, magnetic quantum number will tell us about the orbital of an atom. Now we want to calculate the number of orbitals in a shell or a subshell. So what we will do? We will write number of orbitals in a shell or number of orbitals in subshell. So we have the two terms for calculating the orbitals in a shell and a subshell. Now how do we calculate the number of orbitals in a shell? For calculating the number of orbitals in a shell, we have a formula n square, but if we want to calculate the number of orbitals in a subshell, we have a formula that is L plus 1. So these are the two formulas for calculating the number of orbitals in a shell or a subshell. Now what we will do, we will take different values of n. What are the values of n here? 1, 2, 3 and 4. For the different values of n, we will get the number of orbitals as n square means 1 square, that is equal to 1, 2 square, that is equal to 4, 2 square we will get 4, we have 3 square that is equal to 9, and we have 4 square that is equal to 16. So these are actually the value of number of orbitals in case of a shell. Now what we want to determine? We want to determine the number of orbitals in a subshell. So for calculating the number of orbitals in a subshell, what we will do? We will take the values of L over here. L0, 1, 2 and L equal to 3. Now we want to calculate the number of orbitals in a subshell. What we will do? We will put value of L, that is 0 into 0 plus 1, 0, 1 into 1 plus 1, that is equal to 2, 2 into 2 plus 1, that is equal to 6, 3 into 3 plus 1, that is equal to 12. So 0, 2, 6, 12, these are the number of orbitals in the subshell, and 1, 4, 9, 16, these are the number of orbitals in a shell. So magnetic quantum number basically tell us about the number of orbitals and the direction in which the orbitals are oriented. So it is all about calculating the number of orbitals in a shell or subshell. If someone wants to copy it, please copy it now. Now what we will do, we will check the values of L for a particular value of M. So we have here we have different values of L and here we have different values of M. Here L will represent the azimuthal quantum number and M will going to represent the magnetic spin of an atom. So for different values of M, we have different values of L and M. So first I will consider L equal to 0, 1, 2 and 3. Now for different values of L, we have the different values for the magnetic quantum number, and these values are, for 0 it is 0, and for 1 value is 0 and 1, for 2 value is 0, 1 and minus 1, for 3 the value is 0, 1, 2, and in this direction we will get minus 1 and minus 2. So these are the values for magnetic quantum number. These will be in the positive side and as well as in the negative side of a number line. So these are the values of M. And it will tell us about the magnetic quantum number. Now, what will be the direction of orientation of the particular orbits in the magnetic quantum number? Third factor is the magnetic quantum number will going to specify the direction of orientation of the orbitals. So now we will learn about the direction of orbitals. So magnetic quantum number will going to tell us about the direction or orientation of an orbital in the three-dimensional space. So magnetic quantum number, it will specify orientation of orbitals in three-dimensional space. So magnetic quantum number will going to specify the particular orientation of an orbital in three-dimensional space. So first I am considering S orbital. So what about the S orbital? In the S orbital, if I want to find the direction of the orbital, it will be along x-axis, y-axis and z-axis. So how will we draw the orientation diagram? It will be in x-axis, z-axis and y-axis. So on calculating the orbital of the atom, what we will see the shape come out to be as a sphere. So we can say that the S orbital will having a shape that is spherical in size. So what we will get? We will get spherical shape. Now proceeding to our next dimensional figure, we will consider p orbital. If I talk about the p orbital, what actually happens in the p orbital? We have value of L equal to 1 and M will have a 3 values, that is 0, +1 and -1. These are the set of azimuthal quantum number and magnetic quantum number for p orbital. And if I talk about s orbital, here we have values of L equal to 0 and M is also equal to 0. Now what we want to know? We want to know the shape of degenerate orbitals in case of p orbital. So what we will get? Firstly, we want to know about the p xy, p yz and p zx. We will get the three-dimensional diagram in this way. So firstly, I am considering the pxy. So what will be the shape of the orbital? Here we have x-axis, here we have z-axis and here I am drawing y-axis. Now what will be the shape of the orbital in case of pxy? What we will get? We will get one lobe here and one lobe here. Now we want to determine the shape of the orbital in case of pyz. So again we have x-axis, we have z-axis and we have y-axis. Now what will be the shape of orbital in case of pyz? So in case of pyz, what we will get? We will get one lobe here and one lobe here. Now proceeding to our third case, the third case is pzx. What will be the shape of orbital in case of pzx? Again we will draw x-axis, z-axis and this is our y-axis. So the shape of orbital in this case will be pzx. So value of p for particular value of L is -1, 0 and 1, and for the 3 spin magnetic numbers, what we will get? We will get the 3 diagrams for the orientation of the orbitals in a atom. So it is all about the s orbital and p orbital. So what we can conclude from here, the diagram represented here is not spherical in shape, in spite of being it is dumbbell shaped. So what we will call the diagram for a p orbital? The p orbital diagram will be the dumb shell, dumb bell diagram. And For the s orbital, we have a diagram that is spherical in shape. So we may conclude the for s orbital, the value will be in spherical shape. And for the p orbital, what we will get? We will get the dumbbell structure. So it is all about the s orbital and p orbital. Now we are proceeding to our next orbital, that is d orbital and f orbital. So coming to our next topic, that is d and f orbital. Now in the magnetic quantum number, we are on our third category, that d orbital. If I consider the value of d orbital as L equal to 2, so we have particular values of m, that is 0, 1, 2, and in this direction we have again 5 values, -1, 0, 1, 2, and in this direction we have -2. So for L equal to 2, we have the 5 values for m, and these values are 0, 1, 2, and in the negative direction these are -1 and -2. Now we want to draw the orientation orbital diagram in 3D space for d orbital. So what will be the values for d orbital? It is d xy, d zx, d yz, d x square minus y square, and dz square. So these will be the values of d orbital, and these are d xz, yz, zx, x square minus y square, and dz square. So we will draw the orbital diagram for the following components. So firstly we will draw the diagram for dxy. So again dxy, it means the orientation will be in the xy form. So which diagram we will get? We will get a single lobe here, one lobe here, and two lobes here. Again we have x-axis, z-axis, and in between it we will get the y-axis. So this will be the diagram for dxy. Now we want to draw the orbital diagram for dzx. What we will get? We will get again x-axis, z-axis, and we want to draw the orbital for dzx. So value for dzx will be, what we will get? Again we will get small lobe in this direction, one big lobe in this direction, and two long lobes in this direction. So this will be the orbital diagram for dzx, and this is again y-axis. Now we are on our third diagram for orbital representation, that is dyz. So what we will get for the dyz? Again x-axis, z-axis, and we want to draw the diagram for dyz. What we will get? We will get one small lobe here, big leaf here, and again it is y-axis. So this is the diagram for dyz. Now I want to draw the diagram for dx square minus y square. So which lobe we will get? we want to draw the diagram for dx square minus y square, we will get all the four lobes in the same orientation. This is for dx square minus y square. Again we have x-axis, z-axis, and in between it we have again y-axis. Now we want to conclude the orientation diagram for dz square. So what we will do, dz square, we will get this here, this lobe here, and in between it we will get the two lobes. So this will be the diagram for the last one, that is dz square. So from this orbital diagrams we can conclude that the shape of the d orbital will be the double dumbbell. So the structure for it will be the double dumbbell structure. Double dumbbell. So this will be the shape of the diagrams for the d orbital. Now we are with our last orbital, that is f orbital. The f orbital is very complex, so it is quite complicated to design the orbital diagrams for f orbital. So it is all about the magnetic quantum numbers here that we have discussed, and we have discussed this phenomena is basically given by Zeeman. So we are with our next term, that what is actually the Zeeman effect. So our next topic is Zeeman effect. Zeeman effect. According to the Zeeman, when we want to split the compact of the orbital, that what we will get? We will get this closed spectral line under the influence of the magnetic field. So the statement for the Zeeman effect is, in the presence of magnetic field, in the presence of magnetic field, the spectral lines split into closed spectral lines. So this is basically the Zeeman effect, in which the presence of magnetic field will split the spectral lines into the closed spectral lines. So this is the Zeeman effect, and this conclusion will be given for the magnetic quantum numbers by Zeeman. Now we are proceeding to our last set of quantum numbers, that is spin quantum number, and it is our fourth quantum number. Fourth quantum number is spin quantum number. So what will spin quantum number specify? It is given by Goldschmidt. So spin quantum number is basically discovered by Goldschmidt, and the spin quantum number will automatically tell us about the spin of an electron in an atom. So it is represented by small s. Spin quantum number will be represented by small s. Now, what will be the spin of an electron? This spin quantum number basically states that if we want to calculate the spin of an electron, so the spin will be first in the anti-clockwise direction. We have two directions, that will be clockwise. For the clockwise direction, the electron will show the +1 to spin, and again for anti-clockwise direction, the electron will show -1/2 spin. So half spin will be shown in clockwise direction and -1/2 spin will be shown by the anti-clockwise direction. So how will we represent the spin of an electron in the atom? See here, suppose we have 1s orbital, then we have 2s orbital, then we have 2p orbital. Now I want to show the spin of an electron in an atom. So one spin will be in positive direction, one will be in anti-clockwise. Again this and this, and the p orbital we can write 1. So two electrons will have a opposite spin in the s orbital, but in case of p orbital this statement is wrong. We have to specify the 1 spin to the electron. So the correct explanation will be so all the spins must be in single direction, and we can split it into the 3 in spite of putting 2 in the one shell. So it is all about the spin quantum number, and if we want to calculate the angular momentum for that spin, so we have again with the formula angular momentum for spin quantum number will be h/2 pi under root s plus 1. So this will be the formula for calculating the angular momentum for the spin quantum number. So it is all about the 4 quantum numbers we have discussed, that is principal quantum number, azimuthal quantum number, magnetic quantum number, and lastly the spin quantum number. Now we will learn about the filling of electrons in the orbital, and again we have 4 rules for this. So now I will show you how the electrons are filled in the orbital. So students, now we will going to learn about the filling of electrons in an atom or filling of electrons in an orbital. So our next topic is filling of electrons. So before filling of electrons, I want to tell you about there are 4 methods, that are the 4 basic methods for filling the electrons in an orbital, and these 4 methods are: first method is known as of-Bose principle. Second method we have Hund's rule. Third method we have Pauli's exclusion principle. And the last method we have N plus L rule. So now we will discuss these 4 methods one by one. Our first method is of-Bose principle. So we will discuss the of-Bose principle first. So our next topic is of-Bose principle. So what of-Bose principle states that? Of-Bose principle states that the filling of an electron in an atom will take place in the manner that the lowest shell will occupy the first atom. That it means the orbitals are filled in the increasing order of their energy. So the of-Bose principle states that orbitals are filled in increasing order of energies. So if we want to fill the energy orbitals in the increasing order, it will be in the increasing order of n. Increasing order of n. Suppose we have different orbitals 1s, 2s, 2p. So what we can conclude from here, firstly we will fill the electron in 1s orbital, then 2s orbital, then 2p orbital. So we can conclude that 1s orbital have a least energy. 1s orbital has least energy. So for the obverse principle, now we can conclude that how will the orbital's energy take place. So here I am writing the diagrammatic representation for obverse principle. It means filling of the orbitals will take place in the increasing order of their energy. So what we will do, firstly we will write 1s orbital, then we have 2s and 2p, then we have 3s, 3p, 3d, then we have 4s, 4p, 4d and 4f, then we have 5s, 5s, 5p, 5d and 5f. Now we have 6s and 6p. So this is the diagrammatic representation of the obverse principle. So now what we will do, we will fill the orbitals in the increasing order of their energy. Firstly I am taking 1s orbital. So firstly the electron will get filled into the 1s orbital, then 2s, 2p, 3s, 3p, 3d, 4s, 4p, 6s, 5d and on 6d it will get end. So what we can conclude from here, the electron will start filling from 1s, then the orbital will follow the same sequence as shown in here, that firstly 1s, 2s, 2p, then we have 3s, 3p, then 4s, we have then 3d. So orbitals are filled in the increasing order of their energy. So this is all about the obverse principle, that how electrons are filled in the different orbitals. So here we have a diagrammatic representation. For obverse principle, what we see here, it is the direction of the increasing of n plus l value. Firstly, electron get filled in the orbital 1s, then electron will go into 2s orbital, then we will follow 2p and 3s, then 3p and 4s. After 4s, 3d, 4p, 5s orbital are filled, and the sequence for the increasing order of the energies will be 1s having least energy, 2s, 2p, 3s, 3p, 4s, 3d. After 4s, 3d we have 4p, 5s, 4p, 5s. After having 4p, 5s, we are having 4d, 5p and 6s. 4d, 5p and 6s. After filling 6s orbital, we are with 4f, 5d and 6p. 4f, 5d. I am writing the sequence here. 6p. Now what we are left with? We are left with 5F and 6D. It means electrons are filled in the increasing order of their energy, and this sequence is shown up here. So it is the increasing order of energy. So this is the sequence for the Aufbau's principle, that how electrons are filled in the particular orbital of their energy. So this lecture is over for today. We will discuss about Pauli's exclusion principle and Hund's rule in our next class. Thank you so much and have a nice day.